Yeah, so in this presentation, I'm going to attempt to go through and demystify quantum Monte Carlo terminology, in particular, some of the terms that are very different from what we see in self-consistent field and quantum chemical calculations, and really the input parameters that control the statistics and final error bars that we get in the quantum Monte Carlo. So what I'm going to do is go through the four main input parameters that control variational Monte Carlo, then diffusion Monte Carlo, and have a couple of bonus items and commentary before we move to our main topic today on the molecular calculations. And as I say, every year we get a few questions around this topic, which is why I'm addressing this now. So first, let's discuss variational Monte Carlo. And the first two parameters I'll discuss is blocks and steps. Excuse me. And of course, these are common, not just to variational Monte Carlo, but really all the Monte Carlo methods. So first of all, what are blocks? Well, blocks are how we subdivide the run. And the run is essentially subdivided into an equal number of equal length blocks. So here in this sketch of our Monte Carlo, we have a 3-box across the run. And although the theory doesn't require that we do this, it's done for a convenience. So what's done is that the average statistical results are written out every block. And in the case of QMCPACK, there's a scalar.dat file that you've seen from the examples. And if you're measuring a more heavy observable than the energy, such as charge density, for example, it goes in an HDF5 file. And also restart or checkpoint information is also written with a period that's a multiple of the number of blocks. So this is a useful convenience. Now, what's inside each block is one or more steps. What is a step? Well, that is one attempt where we attempt to go through each electron actually individually within each Walker by the Monte Carlo method that we're using. So in this case, variational Monte Carlo. And having done one sweep, we then measure properties. And so we see here in this sketch, each block is presumably several hundred steps here if this jiggly line is the energy varying of our individual Monte Carlo walkers. So now two additional important inputs for variational Monte Carlo, the time step and warm-up steps, which is to do with equilibration. So first of all, the time step is what controls the size of the displacement for the proposed moves in the Monte Carlo. And as we've outlined before, the guideline is that you pick an acceptance ratio around 50%. It could be a few tens of percent more or less, but it should never be incredibly large or small for efficiency. And of course, one can do a study of the efficiency for the particular properties you're interested in if one's spending a lot of time doing variational Monte Carlo. So I think that's quite straightforward. And I'd now like to discuss warm-up steps, because this is one way of handling equilibration. And there's a difference between variational Monte Carlo and diffusion Monte Carlo that I'd really like to highlight in this short presentation. So what's done in variational Monte Carlo with warm-up steps is we do that many steps without any property measurement actually before the first block. So because we're not measuring any energies or any other properties, this is comparatively cheap. Variational Monte Carlo doesn't require that we actually measure any properties beyond the magnitude squared of the wave function. And that's essentially what's being done here, why we want to use these warm-up steps. Because if we have initially random or semi-random position for the electrons, it's going to take a number of steps before we start sampling the modulus of the wave function squared, which is what we want to be measuring to compute other properties in the variational Monte Carlo. So what we might do is put in 200 warm-up steps here, for example. And this, because this is actually very cheap, the code will give you timing. One can actually be quite generous here. What I do want to underscore, though, is that the code just takes this as an instruction on what to do. There's no internal statistical tests. This is something that you should do outside, particularly if you skip this or you did a particularly short value, for example. So I've attempted to show that here with the slightly ghosted lines for the energies, right? You don't get to see this in a typical run. Now, one area we've had a number of questions is, how many walkers you have both in variational Monte Carlo and diffusion Monte Carlo. So in variational Monte Carlo, we attempt to pick actually optimum defaults if you don't give the code any other instructions. So how many do we have? Well, by default, we'll put one walker per CPU thread and per MPI task. And provided you don't put more threads than you have CPU cores, this will give the highest throughput and the best use of resources. So just as an example here, if we specify I want one thread and then do an MPI run -N4, and this is probably what you are doing in the virtual machines, that will give you 4 walkers unless you request any more. If we think about doing more of a production size calculation or a more challenging system, let's say 8 threads, 64 MPI tasks. Well, if we've done the maths right here, we'd have 512 walkers. And what I'd recommend is actually you always check the output. So in the output, after all the descriptions of the system that's being run, when you reach, in this case, the variational Monte Carlo, we attempt to write out just enough in the log file so you can confirm what's being done. So in this case, total walkers is 4. We'll come to walkers per rank in a moment, and you see at the bottom we're then going to do 10 steps and 400 blocks. So this 4 corresponds to the top line, for example. Now you can change the defaults, and this is going to be something that's important for GPU runs, as we'll cover in a bit over a week. You can also specify the total number of walkers that you would like for the entire run across all the nodes. And you can also specify walkers per MPI rank. And this can be useful if you want to write an input file where if you then run it on a machine that's twice as big, you will then get twice as many samples in your calculation. So there's people have different preferences for how to set up the calculations. One thing to note here is that the VMC implementation can now run any number of walkers. That didn't always used to be the case, and is, I think, one of the differences between QMCPACK and a number of other QMC codes, where you're fixed to the number that matches onto the CPU cores that you have. Again, check the output if you're not 100% confident what's being done. Now, how much work is going to be done? How many property measurements going into the error bars of the properties that we're interested in? And this is a place where we had a couple of questions. Well, in variational Monte Carlo, very simply, it's the total number of walkers that we have times the number of blocks times the number of steps. And this actually applies to all properties. You can see there's some extra notes here if you really want to tune a calculation for maximum efficiency. And of course, what this total means is that if you were to, for example, double the number of walkers and halve the number of steps per block, you would get the same statistics for those properties, but you would have changed the shape of the run to perhaps better fit the computational resources you have. And of course, if you wanted to then halve the error bar, you could increase either the block count by 4, or the number of steps by 4, or the number of walkers by 4. And that would give you a factor of 2 reduction in the error bar because of the square root. So that's variational Monte Carlo. Now, what about diffusion Monte Carlo? Well, again, we have the input of blocks and steps where the run is divided into equal length blocks. So again, I've shown 3 here in the sketch that I showed when introducing diffusion Monte Carlo. And again, summary statistical results are written every block. I'll note that in diffusion Monte Carlo, we also write out a step-by-step track of the energies and walker counts that will be useful for showing some of the traces that I'm showing in the next slides. That gets updated every step. And again, each block consists of at least one step in the Monte Carlo. And difference here from variational Monte Carlo is not only do we attempt to move each electron in each walker in one step, but we then are required to measure the energy, because we need that to evaluate the diffusion Monte Carlo algorithm, and then decide how are we controlling the population of walkers, and then we also measure the properties. And of course, for diffusion Monte Carlo, we need typically thousands of walkers, and I've attempted to show that we might have many walkers per CPU in this sketch here. So now, what about the time step and warm-up steps in diffusion Monte Carlo? And there are some important differences here from variational Monte Carlo. So first, in the time step, yes, again, it controls the size of the displacement for the proposed moves. But if we think back to how we derive diffusion Monte Carlo, there's actually a time step error that comes in due to actually a Trotter discretization, whereby we are going to have to take small time steps in order to accurately compute that Green's function and have a small error. So what that means in practice is that the time step might only be 0.01 compared with 0.5 atomic units for variational Monte Carlo. And then the final acceptance ratio should be very high, say 99.9% for accuracy. And of course, as we've covered, one would eventually do a series of runs at different time steps and extrapolate properties to zero time step. But generally, one would start with always with a very high acceptance ratio in order to ensure that the energy and other properties are accurate. Now, what about warm-up steps? And there's an important difference with variational Monte Carlo here, because the warm-up steps are not done before the first block, right? So the warm-up period is actually included in the output. Why is that? Well, in the warm-up step period here, it has a slightly different meaning. And that is, it's a period of a number of steps during which we strongly control the population. And this actually helps make the equilibration process efficient. So this is the time when we're starting from a high energy and we're shooting down to a lower energy where the ground state is to start sampling the proper ground state wave function. And if we don't control the population strongly, what happens is that it will shoot up and you can potentially run out of memory here, for example, and it certainly be inefficient. So the population is very strongly controlled in this process, and you shouldn't include it when you compute your final statistics. Again, it doesn't actually check the equilibration is completed. This is just instructions to the code, and it's on us to do that analysis. So what I'm attempting to show here is a different behavior from VMC. We have our blocks running here, and there's going to be some period of warm-up steps that we've input during which we're strongly controlling the population. Now, I didn't show the shoot down in energy in the sketch, so let me show this now for one of the real runs that I showed a week ago. So this is a real run on a bulk vanadium. So this is energy against step in the simulation. So this is plotted from that dmc.dat file I mentioned. And we see here this initial propagation down in the energy over maybe 100 or so steps in this case, after which, by eye, we can see we're sampling around some average. So what we might have in this run, and I didn't go back and check what was actually done in this publication, but maybe we'd have set 200 warm-up steps in this calculation and throw away the first 400 from our final statistics to be very conservative. And what other parameters might we set? Well, this run had 3,000 walkers. That's one thing we know from the paper. And they had at least 8,000 steps. So to do a run of the same shape, we might have 100 steps a block and 80 blocks. Obviously, one can reshape that depending on the computational resources one has. Now, how many walkers do we have in diffusion Monte Carlo? Well, here we actually want to specify the size of the ensemble. We want to input the total number of walkers that we have, because that's an important parameter to control any population control errors, for example. So the way I recommend you do this is by specifying either the total number of walkers overall, or specifying the number of walkers per MPI rank. And I mentioned that if someone's handed you a really old input file, well, we used to have a parameter called walkers on its own, which we've now deprecated because that was a little bit confusing as to what the normalization was. If you read the manual on diffusion Monte Carlo, and I'll have a pointer to this in a moment, you'll see you can also specify the target number of walkers, which is the goal for the average population in a diffusion Monte Carlo run. QMCPACK attempts to make reasonable defaults, and sensible choices for runs. So this is actually something you don't normally actually need to set because it will default to the initial number of walkers if you're specifying it through here on the top line. But that's another way you can go in and set the number of walkers that you'd like to see. Of course, in the background, QMCPACK is going to be load balancing these walkers across all the computational resources that you have access to. And again, if you want to confirm what's actually going on, go in and look at the output. So here it says DMC batch driver running with here 128 walkers. And we see it says walkers per rank is 32 by 4. So each core in this, or each MPI task in this case has got 32 walkers, and you can see 10 steps and 200 blocks. And I think this is actually the water example that I had in the first presentation. And again, actually every QMC code runs a little bit like this because by necessarily to run diffusion Monte Carlo, you have to be able to have any number of walkers. So how many property measurements happen in diffusion Monte Carlo? Well, it's similar to variational Monte Carlo, but not exactly the same because of the variable population. So very approximately, it's the total number of walkers that you input times the blocks times the steps. But this would only be true if the population was very closely controlled around total walkers. And in a healthy run, it could be 30% above or below that. So this is where you use QMCA to compute the averages and totals from your actual run. But this is sort of a rule of thumb you can use when planning a run to work out how costly it might be. And as before, just as with VMC, if you want to reduce the error bar by, say, a factor of 2, you could increase the block count by a factor of 4 or increase the number of walkers by a factor of 4, for example. Now, one additional setting that we come across is the term samples. And currently, this is only generally applied to wave function optimization, although we're working to make it more widely available across the other Monte Carlo methods. And this is the number of measurements of energies and wave function gradients that are going to be fed into the optimizer. And there is an advantage here because what will happen if you specify samples and blocks, QMCPACK will compute the correct step count given the number of walkers that you have to get that number of samples. So this lets you uniquely specify the amount of work that's going to be done for that wave function optimization. So that will run the same however many nodes you're running on, for example. I'll note that we try to be very friendly here, and we will overshoot a little bit in order to match up with the number of walkers and blocks that you've got requested. This can, of course, be quite a large number. It might be start with 1,000 for a small system, could be 100,000 or 1,000,000 even, very readily if we're trying to do a very precise wave function optimization. Now, I know that some of you are thinking, yes, this would be very useful to have to specify the total amount of work in really any of the Monte Carlo methods, and that's something we're working to implement right now. So I think QMCPACK will do it, but Nexus won't right now, but that's something we're working to add. It just didn't make it for the summer school. Again, some people like to specify the total amount of work. Some people like to specify blocks and steps. So there's different ways of running the code. So just to summarize here, you can control the number of measurements in variational Monte Carlo and diffusion Monte Carlo by the combination of blocks, steps, and the total number of walkers. And I wanted to highlight this because every so often someone has come to us and said, well, I did a very accurate calculation. I had 1,000 blocks. And of course, on its own, that's not enough to tell us how many samples and statistics were accumulated in the run. We also need the step count and the number of walkers. So it's the product of all of those which is going to give us the final error bar. So maybe that 1,000 block run was actually very, very accurate statistically, but perhaps it wasn't. So we always need the combination of those when discussing how many samples came into a calculation. Just a little bit more general commentary before I stop here and hand over to Amanda. Just in general, QMCPACK is going to respect your inputs where it can, and it's going to warn or abort if it can't satisfy what you've requested. And we try to have very good defaults for any unspecified parameter, just like any other electronic structure or quantum chemistry code. And we also try to include enough in the output that you can confirm what is being done. So my recommendation here is to take advantage of these defaults and keep inputs as simple as possible. Sometimes I've seen people have inherited an input file with lots of settings, and we can't necessarily tell unless comments were added, which of those were actually essential or which of those were just copied in. So my recommendation, and this is what I do, is just keep the inputs as short as you can. Now, of course, there are more inputs to set up a variational and diffusion Monte Carlo calculation than what I've gone in here. And sometimes those are used to really squeeze out the maximum efficiency from the runs, but they're only really needed in sort of extreme cases, or perhaps when one is doing a research calculation into quantum Monte Carlo methods. But we do believe at the minute that actually all the input parameters are fully described in the documentation up on Read the Docs. And there's a whole section there on the methods, which includes tables of the input parameters for each quantum Monte Carlo method, and also some additional explanation. So if you see something and you're wondering about the meaning, just go in there and do a search and you should find it. So I hope this was a useful short presentation on how one can control the statistics in a quantum Monte Carlo run.